Imagine you want to travel from 0 to 1. Instead of directly reaching 1, you decide to approach it by dividing the remaining distance in half at each step. So you take half the distance, then half of the remaining half, and continue this pattern. After 8 steps, you find yourself at approximately 0.9961, very close to 1, but not quite there. This process follows a clear pattern. Each step is exactly half of the remaining distance from the previous step. We can write this pattern mathematically as the sum of 1 over 2 to the power of k, where the Greek letter sigma denotes summation. The index k ranges from 1, the first step, to 8, the final step in this case. Now, what happens if we don't stop and continue this process indefinitely with an infinite number of steps? Will we eventually reach 1? The short answer is yes, we will reach 1. But let's take a step back and understand why exactly. First, let's introduce the concept of a partial sum. Each finite sum at a particular step is called a partial sum. The first step corresponds to the first partial sum, denoted as S sub 1. The second and third steps correspond to the second and third partial sums, respectively. As you increase the number of steps, your partial sum gets closer to 1. Now let's have a closer look. You already know that by taking more steps, you can get arbitrarily close to 1. In mathematics, we can precisely define this closeness. Let's define the closeness to 1 as the green region you see here, and let's call it epsilon. You can make epsilon as small as you want, but it must be larger than 0. Note that the arrow representing the distance to 1 is greater than epsilon. However, if we take another step, corresponding to the ninth partial sum, the distance to 1 becomes smaller than epsilon. We can write that statement as an inequality. The absolute value difference represents the distance between the ninth partial sum S sub 9 and the value 1, which is our target. The inequality states that this distance is less than epsilon, our chosen measure of closeness. If we select a smaller epsilon, then the inequality indicates that the distance between S sub 9 and 1 is now greater than epsilon. However, by taking another step and considering the 10th partial sum, S sub 10, we find that S sub 10 minus 1 is smaller than epsilon, meaning the distance becomes smaller than epsilon once again. So no matter how small we make epsilon, with each additional step we take, the distance between our partial sums and the target value of 1 continues to decrease. This shows that the series is converging towards 1, as we can always find a partial sum that is within any desired closeness epsilon of 1. In mathematics, a convergent series is defined as follows. A series converges if there exists a real number L, such that for any arbitrarily small epsilon, there exists a positive integer capital N, such that for all values of n greater than capital N, the absolute value of the difference between the nth partial sum S sub n and the limit L is less than epsilon. If the series converges, the unique number L is called the sum of the series. This definition means that as the number of terms in the series approaches infinity, the partial sums get arbitrarily close to the limit value L. In our case, the limit is 1, and as we saw, by taking more steps, we can make the partial sums as close to 1 as desired. Hence, the series formed by repeatedly dividing the remaining distance in half is a convergent series, and the sum of the series is 1. If you enjoyed this video on convergent series, consider subscribing to my channel. Thank you for watching.